This meeting is being recorded.
In this video, we're going to cover the first half of section 7.7, and that will specifically review E2 elimination reactions and the regioselectivity. So how do we determine what product will be produced? What region of our compound will have this elimination occur depends on whether or not our strong base that's used is either a bulky or a small type of base. So depending on what type of base we use, we're going to generate one product or another. So here we have our tertiary alkyl halide, our substrate, and if we have more than one beta carbon, so that would be a carbon that has a beta proton that could be deprotonated by a strong base, we can have more than one product. So we see here, this is our alpha carbon, so we have this beta carbon here, or this beta carbon here, each of which has either 2 protons or 3 equivalent protons that could be removed. So what we see with this non-bulky base here, the sodium ethoxide, is that our product that is more highly substituted, called the Zaitsev product, is going to be our major product. This is more stable, as we've seen in previous discussions, because it's more highly substituted. So overall, this would be our more produced product. And then we have our minor product. So this is minor over here. This is our Hofmann product. And again, that would be due to elimination of one of these protons over here to generate the least substituted product possible. So again, depending on what proton is removed, what area or what region in your molecule will have this elimination and pi bond formation occur, that is dependent on what type of base is used. So we can predict or even control a reaction by carefully choosing which strong base we use. So let's take a look at some common bases that can be used and some data that has been produced. So we see here with a non-bulky, unhindered base like ethoxide here, this would favor the Zaitsev or more highly substituted product. Then when we have either a tert butoxide or even this more highly hindered type of sterically hindered base, then we have a majority of our product that is favored to be Hofmann. And again, that has to do with sterics and the fact that this bulky and hindered base, so this is the bulkiest down here, it would be unable to deprotonate our alkyl halide in an area that the more highly substituted alkene would result. So we will continue with this discussion here on regioselectivity and sterics with some more common bases that are bulky down here. So we have these non-nucleophilic bases. They're not really able to function as a nucleophile because of these steric hindering groups around the lone pairs that function as a base. So we have our potassium tert butoxide. Sometimes that's written this way. Then we have diisopropylamine in the middle. You can see that's bulky. And then we have our triethylamine, which has that nitrogen surrounded by 3 ethyl groups. So let's see if we can predict products for these 3 reactions shown below. So we're told that they undergo E2 mechanisms. So step 1, we should find our alpha carbon and then look for any beta carbons close by. And then our third down here. So this beta carbon does not have any protons. attached that could be removed in this elimination. So we'll discount any products that could be formed at that site through elimination. But we do have this non-bulky, non-sterically hindered base. So we expect that our Zaitsev product would be our major product. So that would be if one of these protons here were removed. So there's two equivalent protons. So let's draw our product. So we have those two methyl groups there, the other methyl group up top here. The chlorine was removed. That's our leaving group. And then one proton on this side over here. So this would be our major product, the Zaitsev product. And then our minor product would be if one of these beta protons was removed. So we would have our less highly substituted product result, and it would look something like this. So let's see what happens. We have the same substrate given in each of these examples here, the same starting material, a tertiary alkyl iodide here. And first up, we have a non-bulky, non-sterically hindered base. And then down here, we do indeed have tert butoxide. So we have a sterically hindered base. So both of these will generate the same two products, but we're going to see that what is the major in the first case is going to be the minor in the second. So again, we'll identify our alpha carbon, and then we have these two equivalent beta carbons over here, and then another one here. So again, we have our two beta carbons and then the beta hydrogens that we can remove. So with a non-sterically hindered base, we should see that the more highly substituted Zaitsev product would be our major product. And then the least sterically hindered Hoffman product would be our minor product. And then, like I said, the opposite would happen with this bulky base. So down here, this would be the minor product due to tert butoxide being used. And then over here, this would be our major product. So we'll review more practice problems in the later on in other videos so that we can master how to predict products and determine regioselectivity. So we'll continue with part 2 of this section and determine stereoselectivity of these elimination reactions.